Imagine you were in an elevator. The doors slide shut, the car jerks upward, and for just this split second, you feel like 10 pounds heavier.
Oh, yeah, your knees buckle just a little bit.
Right. And you have to wonder, did gravity just suddenly change its grip on the planet?
Yeah.
Or is something else entirely assaulting your feet?
It's a moment we've all experienced, but, we rarely actually pause to decode what's mechanically happening beneath our shoes. We just sort of accept it as a quirk of modern life.
Yeah, we totally do. And that tendency to just accept things without looking closer is exactly why we are so thrilled to welcome you to today's deep dive.
Absolutely.
Our mission today is to take a highly unique set of source material, specifically this really fascinating physics textbook called The World in Motion, a clear guide to foundational physics.
Which surprisingly actually concludes with a short fiction story.
I know, right?
Cool.
So cool. And we're going to use this book to completely rewire how you view your everyday surroundings. We're moving entirely away from treating physics as this tedious hunt for a magic formula.
And that shift in perspective is everything. Because I think people often think of physics as something, confined to sterile laboratories.
Yeah, with perfect vacuums and frictionless surfaces.
Exactly. Where scientists in white coats write these arcane symbols on chalkboards. But it is happening right now in the room with you.
It really is.
It's happening when your morning train leaves the station or when your coffee cools on your desk, and definitely when that elevator pushes against your feet.
Okay, let's unpack this, because our sources make this incredibly compelling argument right out of the gate.
Yeah.
To understand how the world moves, we first have to understand the inherent flaws in how we look at it.
Right.
The book starts with this foundational philosophy of measurement, specifically the idea that every measurement we ever make has strict limits.
Yeah, the concept of significant figures, which, it's not just a tedious rule for high school students. It is this fundamental philosophy of scientific honesty.
Honesty in math, yeah.
Yeah. The text points out a very practical reality. If you are using a standard plastic ruler marked only in millimeters, you physically cannot justify reporting a measurement down to, 1/1,000,000th of a millimeter.
Because you just can't see it.
Exactly. You simply don't have the optics or the tools to claim that level of detail.
Wait. So science isn't about finding the perfect, exact truth. If I upgrade my tools, say I ditch the plastic ruler and use a high-end digital scale with 5 decimal places, isn't that automatically more accurate?
Well,
Because it feels like if I try to measure a squirming puppy with a laser ruler, the tool might be incredibly precise. Shouldn't my data be too?
that squirming puppy is exactly why pretending your data is flawless is bad science.
Oh, really?
Yeah. The laser might bounce back a reading with 8 decimal places, but the reality of the puppy's motion introduces an inherent, unavoidable uncertainty.
Because the puppy is wiggling.
Right. The text warns explicitly against claiming what it calls false precision. So when you plug 2 rough measurements into a calculator, the screen might spit out a string of 10 digits.
Yeah, you're tempted to write them all down.
But writing down all 10 digits isn't being thorough. It's actually lying about the capabilities of your original tools. Honesty about what a measurement can support is way more important than a flawless-looking number.
Wow. So we have to admit our own blind spots before we even begin to do the math.
Exactly.
And speaking of the math, this philosophy completely changes how the book handles equations. I always looked at physics formulas as these magic spells. You just, memorize the symbols, plug in the numbers, and the universe spits out the answer.
A lot of people do. But the text argues an equation is just a compact statement about a relationship.
Right, and the conditions of that relationship.
Crucially, yes. The specific conditions under which that relationship holds true. They aren't universal commands. They are descriptions of very specific physical scenarios.
The moment that really cemented this for me was looking at the standard equation for displacement. The one for constant acceleration.
Oh, sure.
It's the one with the fraction in it. Displacement equals initial velocity times time, plus 1/2 acceleration times time squared.
A classic.
I spent years thinking that factor of 1/2 was just this random mathematical constant handed down by Isaac Newton himself.
It does look pretty arbitrary on the page, but the book does a beautiful job of demystifying that exact formula. It pulls that 1/2 out of abstract algebra and puts it straight into geometry.
Yes, the graph.
Right. If we want to really understand it, we need to visualize a graph.
Hmm.
Imagine a graph where the horizontal bottom axis is time passing, and the vertical side axis is how fast you are going, your velocity.
So if I'm driving at a steady speed on the highway, my line on that graph is just flat and horizontal.
Correct. And the distance you've traveled is simply the area of the rectangle underneath that flat line?
Base times height.
Exactly. Time multiplied by speed. But if you press the gas pedal and accelerate, your line isn't flat anymore. It tilts upward on a diagonal.
Because my speed is getting higher as time goes on.
Right. Now look at the shape underneath that tilted line. It's no longer just a rectangle.
Right, it's a rectangle with a triangle sitting right on top of it.
Yes. The bottom rectangle represents the distance you covered due to your initial speed. That top triangle represents the extra distance you covered because you were speeding up.
And here comes the magic part.
What is the geometric formula for the area of a triangle?
1/2 base times height.
The 1/2 in the physics formula is literally just the 1/2 from the geometry of a triangle. The acceleration is the slope, the time is the base. When you calculate 1/2 AT squared, you are physically calculating the area of that triangle on the graph.
That is just brilliant. It's a literal shape. It's not a floating digit. It represents physical space on a graph. I mean, once you see that, the wall of intimidating symbols just completely crumbles. It's just triangles and rectangles.
If we connect this to the bigger picture, you start to realize that every number, every variable, and every fraction in a physics formula has a physical, tangible origin.
They aren't abstractions at all.
No, they represent physical realities subject to the very limits of how we measure them.
So let's take that physical reality and apply it to something we measure intuitively every day, our daily commute. The sources use this incredible example of a cyclist's reaction time to break down how motion happens in the real world.
It's a great scenario. It really forces you to separate the decision to stop from the physical act of stopping.
Right. The setup is that a cyclist is cruising along at 6.0 meters per second, and suddenly a hazard appears in the road. The book notes that it takes the cyclist 0.70 seconds to react and hit the brakes.
Which honestly sounds incredibly fast. 0.7 of a second is less than a heartbeat.
It sounds instantaneous.
Yeah.
But when you do the math, multiplying that 6.0 meters per second by the 0.70 seconds of reaction time, the cyclist travels 4.2 meters before the brake pads even touch the wheel.
4.2 meters.
That is the entire length of a crosswalk.
And this brings us back to the mechanisms of how things actually work. Why does it take 0.70 seconds? It's not just a delay in the bike, it's a delay in the human.
The biology of it.
Exactly. Light from the hazard has to enter the eye, the brain has to process the danger, a chemical signal has to fire down the spinal cord to the hand, the muscles have to contract, and then the tension in the brake cable has to overcome physical friction.
All before the braking process even begins.
Right.
You are covering a car length of distance completely blind to any slowing down. I mean, it makes you realize how much faith we put in our own neurobiology when we navigate traffic.
It really highlights that motion doesn't pause while we think. And just as our brains have to contend with physical realities, our bodies have to contend with hidden forces. Let's return to your elevator example from earlier.
Yes, the heavy feeling. The book calls this apparent weight. It explains that if a 50-kilogram person steps into an elevator and it accelerates upward at 1.2 meters per second squared, they feel like they weigh 550 newtons.
But the actual force of gravity pulling down on their mass hasn't increased by a single ounce.
Right. So what is happening?
The key mechanism here is the normal force. We colloquially say we feel gravity, but we actually don't. We feel the floor resisting gravity. When you stand on solid ground, the floor pushes up against your shoes with a force exactly equal to your weight.
But when the elevator motor kicks in to accelerate upward,
the floor has to do more than just support you. It has to physically change your state of motion. It has to push up harder than gravity is pulling down, effectively shoving you upward into the air.
Oh, wow.
That extra pushing force compresses the joints in your legs and the soles of your feet, which your brain interprets as feeling heavy.
The floor is literally assaulting my feet to force me to move.
Yeah.
That's wild. So what happens when that same elevator is coming down from the top floor and suddenly hits the brakes to stop at the lobby? Am I accelerating up or down? Because my speed is decreasing, but the floor is pushing up into me again.
This is one of the most counterintuitive concepts in the textbook. We are dealing with negative acceleration, which most people incorrectly assume just means slowing down.
Oh, that's definitely how I always use the term. Negative acceleration is just a direction, like hitting reverse on a video playback, not necessarily the concept of slowness.
Think about the arrows. Acceleration in physics is a vector. It has a magnitude, how much the speed is changing, and a direction. The positive or negative sign simply indicates which direction the change is pointing on a coordinate grid.
Okay, so if I'm driving my car and I hit the brakes, the force is pointing in reverse while my car is still moving forward.
Exactly. If your car is moving forward, let's call that positive velocity, and you hit the brakes, the force of the brakes is pointing backward. That's negative acceleration. Because the arrows point in opposite directions, you slow down.
Okay, but wait. What if I put the car in reverse and slam on the gas?
Now your car is moving backward, you have negative velocity, the engine is also pushing you backward, so you have negative acceleration. Both arrows point in the same negative direction. So in this scenario, you have negative acceleration, but your car is actually speeding up. The number on your speedometer is climbing, just in reverse.
That completely redefines the term for me. Negative acceleration doesn't mean slowness at all. It just means a push toward the negative side of the grid.
And this brings up a critical reevaluation of what mass actually represents. We tend to think of mass as just how heavy an object is.
Right.
But in Newton's framework, mass is fundamentally a measure of inertia. It is an object's inherent stubbornness. It is the resistance to being accelerated. A heavier object requires a much larger net force to achieve the exact same change in velocity as a lighter object.
I love that word, stubbornness. We've spent this time visualizing these massive tangible interactions. Cyclists pulling brakes, elevator cables hoisting metal boxes. But the sources then take this hard pivot into the invisible.
I do, yeah.
It turns out that the exact same rules of honest measurement and energy transfer apply to the invisible forces all around us.
Thermodynamics and wave mechanics. And the text starts by correcting perhaps the most common misconception in everyday science, the difference between heat and temperature.
Oh, the bathtub versus the coffee cup example. The book states you cannot compare a small mug of boiling water and a lukewarm bathtub by temperature alone and understand what's really going on with the energy.
Right, because temperature is essentially a speedometer for molecules. It measures the average kinetic energy, the microscopic random motion of the particles in a substance.
Okay.
The water molecules in the boiling cup are moving much faster on average than the molecules in the bathtub.
But heat is something different. I was trying to visualize this and think of temperature like the water pressure in a hose. If I have a tiny little squirt gun pumped up to maximum pressure, it shoots a very fast, sharp stream of water. That's high temperature.
I like that.
But the bathtub is like a massive, slow-moving river. The temperature's low, the water is just lazily drifting by.
And heat, in this analogy, is the actual volume of water that gets transferred if you place a bucket in front of them.
Exactly. The squirt gun might be high pressure, but it's only going to transfer a few ounces of water into the bucket. The slow-moving river, because it has so much mass, will fill 100 buckets in a few seconds. Heat is the actual energy transferred. The bathtub contains vastly more total internal energy to transfer because the sheer amount of matter matters.
What's fascinating here is that this principle of energy traveling and transferring applies beautifully to acoustics as well. The text emphasizes a profound mechanical truth about waves. A wave is a disturbance traveling through a medium, but the medium itself does not travel.
It's like dropping a pebble into a still pond. You see the ripples moving rapidly outward toward the shore. But the water itself isn't flowing to the edge. A leaf floating on the surface just bobs up and down.
Exactly.
The water is just passing the energy along like a stadium crowd doing the wave. Nobody leaves their seat, they just stand up and sit down.
That's a perfect analogy. Because waves are just traveling patterns of pressure, they can overlap in the same physical space. This is the principle of superposition.
Okay, what does that mean in practice?
Well, when the peaks of two waves meet, they combine into a larger wave. That's constructive interference. But when the peak of one wave meets the trough of another, they fight each other. They cancel out. This is destructive interference.
Oh, wow. Here's where it gets really interesting for anyone who commutes. My noise-canceling headphones.
Yes.
I always vaguely assumed they just had really thick foam that built a physical wall against airplane engine noise. But they are actively weaponizing this wave interference, aren't they?
They absolutely are. Active noise control is a marvel of rapid computation. The headphones have these tiny microphones on the outside that listen to the incoming sound waves, say the low hum of a jet engine.
And sound is just a pressure wave pushing against the air, right?
Yes. High pressure pushing in, followed by low pressure pulling out. The microchip inside your headphones calculates the exact frequency and amplitude of that incoming pressure wave in a fraction of a millisecond.
That's incredibly fast.
It has to be, because it then directs the headphone speaker to generate a precise mirror image sound wave. When the jet engine wave is pushing high pressure into your ear canal, the speaker fires a low pressure trough at the exact same instant.
Wait, really? So my expensive headphones aren't a wall. It's firing a mirror image sound wave into my ear to destroy another sound wave.
Exactly. The instantaneous displacements add together to equal zero. The air in your ear canal stays still, and you hear silence.
It's an acoustic anti-missile defense system. That is so cool.
It relies entirely on the precise timing and positioning of those wavefronts. And, a similar phenomenon governs how we perceive pitch when things are moving.
Oh, the Doppler effect.
Yes, the classic ambulance siren. When it drives toward you, the siren sounds high and frantic. The second it passes you, the pitch drops into a lower wail.
The key takeaway from the text for me was understanding the mechanism of why that happens, because the physical siren on top of the ambulance is oscillating at a constant frequency.
Right? Right, the actual source never changes its tune.
But because the ambulance is driving forward, it's essentially chasing its own sound waves.
It is driving into the sound waves it just emitted. This physical motion squishes the wavefronts closer together in front of the vehicle. Shorter wavelengths hitting your eardrum mean more vibrations per second, which your brain interprets as a higher pitch.
So the reality of the siren hasn't changed at all, but my perspective as a stationary observer completely alters my measurement of that reality.
Which brings us perfectly to the final and perhaps most unexpected part of our source material. The textbook concludes with a short fiction story called 1 Second Before the Raindrops Stopped.
Yeah, I was so surprised to find a narrative story at the end of a physics textbook, but it does an incredible job of taking these perfect, unyielding laws of visible motion and invisible energy and colliding them with the incredibly flawed human element of science.
It really does.
The story follows two high school students, Mio and Saki. They're setting up a science fair experiment to measure the gravitational acceleration of a falling water drop.
It's a classic kinematic setup. They have a dripping nozzle, a strobe light or fast camera, and a ruler placed in the frame to track the distance the drop falls over time. We established earlier that gravity accelerates objects at roughly 9.8 meters per second squared.
Right. But when Mio and Saki plot their data points on a graph, the line doesn't match the textbook. Their calculations yield this bizarre acceleration of 11.6 meters per second squared.
It's a massive discrepancy. And this is where the textbook forces the reader to confront the psychology of measurement we discussed at the very beginning.
Because Mio looks at the graph, sees 3 data points veering wildly off the expected line, and feels this wave of panic. She actually considers just deleting the bad data.
Which happens more than you'd think.
The story reveals she has this lingering anxiety from a past project where she felt pressure to hide messy results just to guess the approved number the teacher wanted. She just wants the graph to look clean and perfect.
It is a temptation every scientist, from high school to professional laboratories, has faced. When the messy reality of the squirming puppy doesn't match the clean math, but their teacher, Mr. Kurakawa, steps in and shifts their perspective. He challenges them to figure out why the data strayed, rather than just erasing it to feign perfection.
So they go through this rigorous, exhausting checklist. Is the nozzle vibrating? Is the drop sizing consistent? Are the lights causing a thermal draft?
Finally, they discover it is a perspective error. The camera they were using wasn't perfectly level, it was tilted downward at a slight angle. Furthermore, the ruler they used for scale wasn't in the exact same plane as the falling water, it was placed a few centimeters behind the drop.
So because the camera was looking down and the ruler was further back, the distance the drop appeared to fall in the video was optically distorted.
Yes. And once they square the camera perfectly to the plane of motion and align the scale with the droplet's path, they run the trial again. Saki calculates the new data and gets 9.7 meters per second squared.
As she jokes in the story, Earth had returned to normal service. But the real emotional payoff is what they decide to do at the science fair. They don't just present the flawless corrected graph. They build a display showing both the distorted 11.6 data and the accurate 9.7 data side by side.
They use their initial failure to prove to the judges exactly why camera positioning and perspective are critical variables in observational science. It perfectly encapsulates Mr. Kurakawa's overarching lesson, which is the ethos of the entire textbook. Measurement is not a contest to guess the approved number. It is an argument about how much confidence a number deserves.
That line is so good. Discarding data simply because it challenges your hypothesis isn't just cutting corners, it destroys the integrity of the process. So what does this all mean for us? Is the textbook basically saying that being a good physicist means being comfortable with being publicly wrong?
In a way, yes. An unexpected discrepancy isn't a failure to be hidden. It's a neon sign pointing toward a variable you haven't accounted for yet.
It actually changes how I look at mistakes in general. It frames being wrong not as a character flaw, but as the primary engine of discovery. Mio's tilted data wasn't a lie. It was a perfectly faithful recording of a flawed setup.
Understanding that the world is messy, our tools are limited, and our perspectives are easily distorted is the first requirement for doing actual science.
Well, we have covered some truly incredible ground today. We started by accepting the limits of our millimeter rulers, then visualized the hidden geometric shapes hiding inside our equations. We decoded the delayed mechanics of a braking cyclist and the pushy normal force of elevator floors.
It's been quite a journey.
We watched invisible sound waves destroy each other inside our headphones. And finally, we saw how the integrity of a high school science project proves that how we measure the world is just as important as what we measure.
The unifying theme is that physics is not a wall of esoteric math. It is a language. It is a tool set designed to help you listen more closely to the story your environment is constantly telling you.
But before we let you go, we have to fulfill our promise and leave you with one final, deeply provocative concept from Chapter 13 of the source material. We've talked extensively about how energy transfers and changes forms, like sound waves and heat. But the book emphasizes that energy conversion is a one-way street.
The law of conservation states that energy is never created or destroyed. It is always conserved. However, the text highlights a darker corollary. While energy doesn't disappear, it does permanently degrade.
It degrades into less useful forms, specifically dispersed, low-temperature thermal energy, heat. The book points out that every single time energy is converted from one form to another, some of it is irrevocably lost to the surrounding environment due to friction, resistance, and mechanical inefficiency.
Highly organized, concentrated energy, like the chemical energy in a battery or the kinetic energy of a speeding car, is highly useful. We can do work with it. But when that energy scatters into random microscopic thermal vibrations, it becomes incredibly difficult to gather back up and turn into anything useful again.
I want you to truly ponder the implications of that mechanism. Every single time you step on the brakes in your car, the friction of the brake pads converts your kinetic motion into heat that dissipates into the asphalt. Every time your noise-canceling headphones generate a wave, the battery drains, radiating slight warmth against your ear. Even right now, as you scroll through this audio, you are permanently converting organized energy into a tiny amount of irreversible heat.
You are quite literally warming the universe.
You are leaving a permanent thermal fingerprint on the cosmos that can never, ever be undone. The total amount of energy in the universe hasn't changed, but its usefulness has permanently decreased just a little bit because of your actions. So the question we leave you with is, what will you do with your highly organized energy today?
That is a powerful perspective to carry with you into the mechanics of your day.
It really is. Thank you so much for joining us on this deep dive. We hope that the next time your train leaves the station, or you hear an ambulance approach, or you watch a single raindrop fall against your window, you'll see the world in motion just a little bit differently. Until next time, keep questioning and keep reading the change around you.